All right, take good notes on this video, and then you turn those in. That's an assignment, the first assignment of the third quarter. Thank you. All right, let me start this, and I'll talk to you. How about that?
One night in 1669, a German alchemist named Hennig Brandt was searching, as he did every night, for a way to make gold. For some time, Brandt had focused his research on urine. He was certain the golden stream held the key. Tonight, his patience would at last be rewarded. He had boiled the urine down to a concentrated paste. Now he subjected it to intense heat. Was this the legendary elixir that would turn lead into gold? Alas, it was not. Brandt had stumbled on the element phosphorus. This is how the discovery of elements began, with people trying to turn the substances of nature into something useful or valuable. But people are naturally curious, so as they worked with these materials, they began to wonder, what is this stuff? What is the world made of? Thousands of years ago, the Greeks proposed that the world is actually made of just 4 elements in combination: air, water, earth, and fire. Today we know that matter actually comes in more than 100 distinct varieties, neatly arranged in the periodic table of the elements. But for most of history, matter was a profound mystery. A 2,000-year detective story in which people across the world were trying to identify the elements and figure out how to use them. It's an amazing story, filled with unforgettable characters. In this series, you'll meet 7 extraordinary scientists whose findings drove the search for the elements. So join me as we retrace the steps of these chemical detectives as they struggle to solve the mystery of matter.
Major funding for the Mystery of Matter Search for the Elements was provided by the National Science Foundation, where discoveries begin. Additional funding provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education, and by the following.
One of the first big clues in solving the mystery of matter came from the discovery of the most immaterial stuff you can imagine: air. Of course, people have always known about air. They could feel the wind on their faces and see its powerful effects in storms. What they didn't know was that there's more than one kind of air. That changed in 1754 when a young Scottish medical student named Joseph Black set out to find a cure for kidney stones. He poured acid on this chalky substance and trapped the air that came out. To his surprise, this air didn't behave like air at all. It was heavier than ordinary air and promptly put out a flame. Black's discovery of fixed air, what we now call carbon dioxide, was a turning point in the history of science. People had long known about liquids and solids. Now, suddenly, they realized there was a third state of matter: gases, of which air is just one example. Over the next 20 years, the exploration of this new dimension would transform our understanding of matter. After Black's discovery, British scientists quickly identified 2 more new gases: hydrogen and nitrogen.
And then in the early 1770s, that astonishing investigator Joseph Priestley discovers all sorts of new airs.
Priestley was a minister by trade, but also an amateur scientist. what was then called a natural philosopher.
He was a great dabbler in things and was constantly getting obsessed with new fields.
Fields like the new science of gases.
Priestley's style of science is very interesting. He's a kind of inspired forager. He's basically messing around with different things to see what will happen. One of the things Priestley did was to pour acid on everything. He collected those bubbles, tested them thoroughly, and discovered all sorts of amazing properties.
By messing around in this way, Priestley discovered 9 new gases, more than anyone else in the world.
He was very much open to chance discoveries. He would stumble across things and he would follow his instincts, and he was always looking for these kind of fortuitous accidents.
One such accident happened in 1767, when Priestley was assigned a new congregation.
They put him in a house that happens to be right next to a brewery, and this turns out to be an incredible stroke of good luck. Priestley, being the constant investigator that he was, would kind of pop over and see what was going on at this brewery.
Just above the vats of beer, he discovered a haze of carbon dioxide bubbling up from the fermenting brew.
And he decided he wanted to do some experiments with their beer. Well, fortunately, they said yes.
Priestley found that if he simply poured water from one glass to another over the surface, the water would absorb the gas rising from the beer. The result was refreshingly bubbly. By 1772, he had invented a better method, generating carbon dioxide and injecting it directly into water.
In the space of 2 or 3 minutes, I can make a glass of exceedingly pleasant, sparkling water. You can't tell the difference between this and natural mineral water.
Priestley had invented carbonation. Remember that the next time you enjoy a soft drink. But with this act, he also set in motion a series of improbable events that would soon overturn our understanding of matter. It began when a British doctor suggested Priestley's windy water might be effective as a treatment for scurvy, a disease that plagued sailors on long sea voyages.
Scurvy was a huge problem for the military during that period, and so the idea that there was this potential solution that also happened to be a tasty beverage was appealing.
In 1772, Priestley addressed Britain's leading scientific organization, the Royal Society, and published a pamphlet describing his method for making soda water. He urged the British Navy to test the potential cure. Quick to pick up on this development was a defrocked Portuguese monk named João Jacinto de Magellan. A distant relative of the great Portuguese navigator, he was now serving as a French industrial spy.
Magellan is in the employ of the French government and is there basically scouting out the Royal Society for interesting items that he might be able to bring back to his bosses.
Sensing a potential military secret, Magellan alerted his handler back in France, Commerce Minister Jean-Charles Trudaine de Montigny.
Trudaine was interested in science, was a member of the French Royal Academy of Sciences, and immediately saw the possible value of this.
Trudaine, in turn, called on one of France's brightest young chemists, Antoine Laurent Lavoisier.
Qui on a l'expéditeur? Monsieur Trudaine. Monsieur Trudaine Montigny. I know your precision when it comes to physics and chemistry, and I'm giving you a chance to be of service to your country. Please repeat these experiments and add your own observations. The value of these discoveries depends on our moving quickly. I hope you will not be long in getting this little work done.
Trudaine probably intended this politely phrased letter as an order rather than a request. Lavoisier really couldn't ignore it.
Though soda water would turn out to be useless against scurvy, this pointed suggestion by a government official acting on a tip from a Portuguese spy would set Lavoisier on the path toward his greatest discoveries. Born into a well-to-do Parisian family, Lavoisier had received a fine education and taken a degree in law. Now 28, he had joined a consortium that collected taxes for King Louis XV.
As a result, Lavoisier became a very wealthy man.
But his true passion was chemistry. Lavoisier spent 3 hours in his private laboratory before work every day and returned there after dinner, often accompanied by his young wife. Marie-Anne Pultz was the daughter of one of Lavoisier's business partners.
Right?
She was just 13 when they were married, but bright, outgoing, and mature beyond her years.
Marie-Anne was virtually his collaborator. She knew English, learned chemistry, assisted Lavoisier in the laboratory. She was an extraordinary person. Had she lived in our own time, she probably would have become an outstanding scientist in her own right.
One of Marie-Anne's most important roles was to create the diagrams and illustrations that accompanied her husband's published work.
Marie Lavoisier's drawings give us the eyes to look directly into Lavoisier's laboratory. We can see the people, we can see the devices, we can see the arrangements of those devices. We can understand what Lavoisier did so much better because of what Marie drew.
Spurred on by Trudaine, Lavoisier eagerly studied fresh translations of Black, Priestley, and other British chemists who had pioneered the study of airs.
The work of these previous experimenters merely hints at what's happening when air is taken up or released by different substances. I shall review all their work, repeat all their experiments, taking new precautions in order to develop a coherent theory. This subject, I believe, is destined to bring about a revolution in physics and chemistry.
What made this new science of air so revolutionary was that it threatened to topple the reigning theory of chemistry, a theory inspired by the mystery of fire. Most chemists believed fire was due to some fiery principle that was given up during combustion. And all our senses seem to confirm this idea. Heat, light, smoke, all are released as the fire burns. By the mid-1700s, this essence of fire had been given a name: phlogiston. Phlogiston was the foundation of chemistry's leading theory for nearly a century, because it seemed to explain things like metals and rust. When iron ore was heated in the presence of charcoal, phlogiston from the charcoal fused with the ore to form metallic iron. When the iron was exposed to air or water, the metal released its phlogiston as it rusted. Other metals went through the same process, forming the green verdigris of copper, for example. Ore plus phlogiston equals metal. Metal minus phlogiston equals rust, or what was then called a calx.
Only there was a problem. The calx was heavier than the metal, even though phlogiston had left the metal. It's lost something and yet it was heavier.
The calx should weigh less than the original metal, but it doesn't. The calx is heavier than the metal.
Though many chemists were aware of this contradiction, they let it pass because phlogiston otherwise worked so well. But Lavoisier was really troubled by this because he was obsessed with the weights of his experimental ingredients.
Lavoisier was very careful to get very good instruments. He probably at one point had the largest and most complete private laboratory on Earth.
With my precision scales, imported from England at great expense, I measure the weight of each substance at the beginning and end of every chemical reaction.
Lavoisier was a master of this balance sheet kind of chemistry. Remember, he was a tax administrator by day. He knew a lot about accounting, and so this kind of ledger keeping was natural to him.
It is a fundamental truth of chemistry that the same amount of matter exists before and after each experiment. Nothing new is created, nothing lost. The whole art of performing chemical experiments rests on this principle.
Today we call this idea the conservation of matter.
When you carry out a chemical reaction, what comes out has to be exactly equal to what goes in.
The total weight must remain precisely the same. If not, there's an error somewhere.
He wasn't the first to assume conservation of matter, but Lavoisier applied this idea more rigorously than anyone had before. And it worked very effectively as a tool of discovery.
The power of Lavoisier's method would become clear in October 1772, when he set out to solve the riddle of why metals gain weight when they form calxes.
Common sense suggested that when things rust, they must lose weight. They fall apart, they become brittle and weak. Lavoisier was interested in actually measuring what happened.
He conducted his experiments in public, relying on a huge burning lens that focused the sun's rays to produce intense heat, while elegantly dressed bystanders watched in amazement. Lavoisier placed a calx of lead mixed with charcoal inside a glass vessel partially filled with water, then subjected it to the intense heat of the burning lens. The result was extraordinary.
As the calx changes back into the metal, it releases a large quantity of air. This air forms a volume 1,000 times greater than the calx it came from.
This startling finding suggested a radical idea. If air came out as the calx changed back into a metal, could it have gone in when the calx was formed? Could air be the reason calxes were heavier than expected? Lavoisier also found that when he burned elements like sulfur, they too gained weight.
There was then no doubt. I realized that the increase in weight occurs because a portion of the air is absorbed into the solid material.
He knew he was onto something very important. He knew that the element did not lose mass, it gained mass. It took up some part of the air.
I felt I must secure my right to this important discovery. So I deposited a note with the secrétaire de l'Académie to remain sealed until I was ready to make my experiments public.
He's discovered what seems to be evidence by weighing things that seem to flatly contradict what the phlogiston theory is predicting.
Despite what our senses tell us, both rusting and burning involve absorbing something from the air, just the opposite of what chemistry's reigning theory held.
It had been known for 100 years that metals gain weight when they become calxes, but no one had bothered to really investigate this anomaly. By focusing so intently on weight, Lavoisier had challenged the very foundation of chemistry, and he'd identified the source of that weight gain. Air was somehow involved.
But was it air itself or some part of the air? And if so, what part? The identity of the mystery gas eluded him for 2 years. He was still stumped in late 1774, but the answer would soon be delivered by Joseph Priestley. By this time, Priestley had begun to study something called the red calx of mercury. Mercury is a strange metal, one of just 2 elements that is liquid at room temperature. But like other metals, it forms a calx, a red solid that pharmacists of the 1700s used to treat venereal disease. Chemists have noticed something unusual about this calx. They could convert it back into metallic mercury simply by heating it. No charcoal, no source of phlogiston was needed. This was theoretically impossible. How could it be? The ever-curious Priestley wanted to know. So in August 1774, he obtained a sample of mercury calx and used his own burning lens to heat it with sunlight.
That reddish substance in turn decomposes, giving back mercury, but also a gas.
Priestley collects this air because he likes to test these gases and to see what properties they have.
If it were his old friend fixed air, the candle would go out.
But what he found about this air was it had quite extraordinary properties.
What astounded me was that the candle burned in this air with remarkable vigor. The flame was bigger and brighter than in ordinary air.
Something in this air seems almost better than normal air, which is very puzzling.
I was utterly at a loss. How could I explain this?
Eh bien, chers amis, buvons à la santé d'Archimède.
Dr. Priestley, have you been to the continent before?
No, this is my first time.
2 months later, on a visit to Paris, Priestley was invited to dine with members of the Royal Academy of Sciences, including Antoine Lavoisier.
J'ai récemment réalisé.
Priestley tells Lavoisier in his very broken French about his new discovery.
Avec les résultats très intéressants. I described this experiment at the table of Monsieur Lavoisier. I never make the least secret of anything I do. Le même air de plum rouge.
Everything that he came up with, every new experiment that he did, even when he wasn't sure what the results meant,
Qu'est-ce que c'est ce plum rouge?
he was constantly sharing that information with as many people as possible.
Mais, à ma grande surprise, I also told them that it produced a kind of air in which a candle burned much better than in common air. Mieux que dans l'air commun. At this, the entire company, including Monsieur and Madame Lavoisier, expressed great surprise. I'm sure they cannot have forgotten these events.
Monsieur Priestley, bien sûr que ce n'était pas l'air fixe.
If you want, I can translate for you.
Merci.
Are you sure that what you found was not fixed air?
Absolutely. I'm not yet sure of what it was.
Lavoisier did not appreciate Priestley's style. He didn't think Priestley brought very much thought to his scientific foraging.
But Lavoisier was smart enough to recognize that Priestley was onto something and take that piece of information and go back to his lab to figure out exactly what Priestley had discovered.
Could this be the gas he was looking for? The one involved in rusting and burning? Lavoisier hurried to the local apothecary to buy his own sample of mercury calx. Back in England, Priestley dithered for months on other projects.
Look what you can do.
Unaware he was in danger of being scooped. Finally, it occurred to him, if this gas he had discovered supports fire, might it also support breathing?
Here we have one of the great discoveries in the history of chemistry, and the scene is kind of amazing. You've got this man and a mouse.
I put a mouse into a glass vessel containing 2 ounces of the air from the heated calx of mercury. If it were common air, a full-grown mouse would have survived in it, perhaps a quarter of an hour.
15 minutes pass. 20 minutes pass.
In this air, the mouse remained perfectly at ease for a full half hour.
That's twice as long as any mouse has ever survived.
I began to suspect that the air into which I had put the mouse was better than common air.
He takes the same mouse, sticks it back under the glass, and sure enough, the mouse survives another 30 minutes in this strange new air. He realizes that something fundamentally different has happened. This air is some kind of super air.
I concluded that this air was between 5 and 6 times better, that is, more breathable than the best common air I'd ever tested.
He finally has kind of convinced himself this air must be safe to breathe if the mouse is doing so well. And so he gets enough courage to actually try it himself.
It doesn't feel any different from common air when I breathe it in. But I feel peculiarly light and easy. In time, this pure air may be useful as a medicine or sold to the fashionable for recreation. Up to now, Only 2 mice and I have had the privilege of breathing it.
As Priestley is conducting these experiments in England, across the channel, Lavoisier is basically going through the exact same experiments.
Lavoisier, realizing that this is essentially the key to the mystery, gets to work on it.
Toi. I found, much to my surprise, that this air had none of the properties of fixed air. A candle burned with a dazzling splendor, and charcoal, instead of just smoldering, threw sparks in every direction.
Lavoisier announced his findings with great fanfare at the 1775 Easter meeting of the Academy of Sciences.
All this evidence convinced me that this air is more breathable, more combustible, and more pure than even the common air in which we live.
And he gives it the name oxygen.
In announcing his findings, Lavoisier made no mention of Priestley's revelation over dinner 6 months earlier.
Now, Priestley is not a shrinking violet here. He hears about this and he objects.
He should have acknowledged that my account over dinner led him to try the experiment. One should not put one's scythe into another man's harvest.
I admit I was not the first to do these experiments. That claim goes to Mr. Priestley. But from the results, we have drawn diametrically opposite conclusions. I may be criticized for having borrowed from the work of this celebrated philosopher, but I trust that the originality of my conclusions will not be challenged.
Lavoisier was right. While it was Priestley who made the discovery, it was Lavoisier who grasped the implications of this new gas.
Toi.
Lavoisier was the only one who understood what was going on. Perhaps he didn't understand perfectly, but the moment that new element, which we call oxygen, was there, he picks it up and he runs with it.
Over the next 15 years, Lavoisier would show that air is not a simple substance, as the ancients believed, but a mixture of 2 newly discovered gases. That water, too, was a product of 2 gases, and that fire is not an element, but a process of combining with oxygen. Even the solid substances the ancients had lumped under the heading earth were now seen in a new way.
Metals like iron and tin and lead had been known for centuries, but in the era of phlogiston, they were thought to be compounds because they had phlogiston in them. Lavoisier had turned this picture upside down. He showed that by stripping away the oxygen from the ore, you got down to the simpler metal within. The metal, not the ore, was the element.
So all 4 of the ancient elements, air, water, earth, and fire, had been abolished, thanks to the discovery of oxygen.
Once you accept the existence of oxygen, the main difficulties of chemistry appear to evaporate. Well, if all of chemistry can be explained without phlogiston, in all likelihood, it doesn't exist.
For years, many chemists, including Joseph Priestley, refused to abandon the old theory. What finally won the day was the textbook Lavoisier wrote in 1789 to spread his new chemical theory. As it was adopted around the world, phlogiston quietly passed into history.
So the old chemical system has been essentially destroyed.
Though Lavoisier is often given most of the credit, it was really both these men, working in their very different ways, who brought about this chemical revolution.
They kind of needed each other in a way. For science to work, you need both kinds of scientists, right? You need the scientists who are great systematizers, and then you need the mavericks and the tinkerers who are going to open up new doors for discovery.
One of the doors Priestley and Lavoisier opened was a fresh way to tackle that old question, what is the world made of? It was clear now that rocks of every conceivable variety might harbor undiscovered elements chemically fused with oxygen.
People realized that if they could release oxygen from other substances, what was left behind might be some of these missing elements that everybody knew must be out there.
How many more elements might you find by stripping away the oxygen that like to bind to so many things?
Lavoisier's textbook included the first modern list of elements, 33 simple substances. Some, including light and heat, were later found not to be elements, but it was a start, and it served as a challenge to other chemists.
Now that they knew how to look for them, chemists began to ask, what are the elements? The question had never been asked before in exactly that way. And so the discovery of oxygen really served as a starting gun for a worldwide race for new elements.
All over the world, chemists and amateur collectors responded to Lavoisier's challenge, rapidly identifying 15 new elements. From Sweden to Mexico, Connecticut to Siberia, the discoveries kept coming, sometimes as many as 4 in a single year. And few things could bring a chemist more glory than identifying a new element.
Well, certainly, Lavoisier was one of the great masters of all time. In fact, this greatest.
One of those who would soon be caught up in the hunt was a precocious chemist from the farthest reaches of England.
Pathetic ideas of phlogiston.
I've just met a remarkable young man whose talents I can only marvel at. He's not even 21 and has been studying chemistry for no more than 18 months, but he's advanced with such strides as to overtake everybody.
Yes.
Oh, his name is Davy, the young chemist, the young everything.
Humphrey Davy was the son of a simple woodcarver from the remote seaside village of Penzance, about a week from London by stagecoach.
Penzance is right down in the far southwest corner of England, and in some sense it was the Wild West, right out beyond the influence of London and its institutions.
When his father died young, Humphrey left school at 16 and took a job as an apothecary's apprentice to support the family. But he never lost his love of learning. He simply resolved to teach himself.
The same year that Davy's father dies, Lavoisier publishes his elementary treatise on chemistry. And young Davy reads this in the original French. He starts keeping notebooks from this very date, and there's a kind of intellectual explosion.
Chemistry arose from the delusions of alchemy, only to be bound by the chains of phlogiston. But through the discoveries of Black, Priestley, and Lavoisier, it has now been liberated.
Davy started doing experiments right away. One of the things he did was to attack Lavoisier's theory of heat.
Lavoisier said it was a material substance called calorique, and Davy didn't believe this.
Davy thought that we could take on the great man. He thought heat was motion of particles, and he thought he could prove this if he could rub 2 pieces of ice together. So no heat would be coming in from outside, and the sheer friction would melt the blocks of ice. And that's what happened. To him and his contemporaries, the experiment was a convincing one.
Davy's findings, written up in his first published work, showed enough promise to land him a post closer to Britain's center of action, in Bristol, at the Pneumatic Institution.
So he leaves remote Penzance to become the assistant and then the director of this new institute. He's only 19, for heaven's sake.
The institution had been founded in the hope that some of the gases discovered by Priestley and others would prove useful in treating diseases. Davy's job was to make the gases and then test them.
I took just 3 breaths of the gas. The first produced a feeling of numbness.
One of the gases he tested was mostly carbon monoxide, the poisonous gas now found in auto exhaust.
He doesn't know exactly what it is, but he makes it and he tests everything on himself. It's amazingly reckless, but it's also very brave.
He acted as if in sacrificing one life, he had 2 or 3 others in reserve. Some days I half despaired of seeing him alive the next morning.
And then he takes his pulse and he says, "I do not think I shall die." And
he's ill for 48 hours, but he survives. On a number of occasions, he does nearly kill himself.
When you've got a career to make, and you're coming from a low point down the social scale, you've got a long way to go, why not take a few risks? Get your way up to the top quicker.
The top Davy had in mind was the very pinnacle of science. On one page of his Bristol notebooks, he wrote his own name next to that of the most famous British scientist of all time.
Newton and Davy. So he has this sense that he and Newton can go at science together. It's not arrogance exactly, it's this tremendous drive. He passionately believes that he will be a sort of Newton in chemistry.
I don't hesitate at all. The great master made a few mistakes.
All his life, that drive is there. Newton and Davy.
In Bristol, Davy sought out a group of literary men whose work would define the Romantic Age, including publisher Joseph Cottle,
Yes.
and poets Robert Southey and Samuel Taylor Coleridge.
Assumption that heat is a simple substance.
Is that what he called caloric?
Precisely.
In looking at that group in Bristol, one of the things I think is wonderful is there was no gap between the writers and the poets and the scientists.
We can discover that the ice melts by friction alone.
Davy, could not the melting have been caused by the temperature of the room?
That's a very good question indeed, one to which I have a ready answer. The air.
Every evening they're going out, they're writing letters to each other, going on walks together, and they're young men with a future. It's an extraordinary group.
In Davy, these romantic poets found a kindred spirit.
Remove the ice from the point of friction, it refreezes.
A scientist who shared their sense of wonder at nature and yearned to reveal her mysterious ways.
Heat must in fact be the motion of particles.
There's an energy, an elasticity in his mind that allows him to seize and analyze all subjects. Living thoughts spring up like turf under his feet.
Early in his research, Davy produced a gas one medical authority had warned was the cause of terrible diseases. He tried it anyway.
This evening I breathed nitrous oxide and experienced a thrilling all over me, more pleasurable than anything I've ever experienced. The objects around me became dazzling and my hearing more acute. Sometimes I responded by stamping my feet. Other times, by dancing around the room and laughing uncontrollably.
As word of his discovery spread, many others, from steam engine pioneer James Watt to the King's own doctor, clamored to try Davy's laughing gas.
Coleridge and Southey both took doses of the gas. It was very much in keeping with this romantic time period.
He's invented a whole new pleasure. It makes you laugh and tingle in every toe and fingertip.
There was a certain amount of recklessness experimenting with drugs. Why not expand your consciousness?
It makes you strong, happy, so gloriously happy. Oh, excellent airbag. I'm going for more this evening.
Davy asked each of his subjects to record their impressions.
The first time I tried nitrous oxide, I felt a highly pleasurable sensation of warmth over my whole body. It was like the feeling I once experienced entering a warm room after returning from a walk in the snow. I felt no desire to move, only to laugh at those who were looking at me.
Davy wrote up their accounts in his first true scientific book. But just as he was finishing the book, Davy's attention was diverted by a discovery that would shake the very foundations of science. In 1800, an Italian named Alessandro Volta announced that he had created a new source of electricity. Up to then, the only sources of electricity had been lightning, which was very difficult to tap, and electrostatic devices like the ones Priestley had used.
You could get quite spectacular effects in the way of flashes and bangs. But you couldn't get sustained power. What Volta did was to establish that electricity was something that you could make a steady supply of, what we called electric current.
Volta's device was incredibly simple. A sandwich of alternating copper and zinc discs separated by pieces of cardboard that had been soaked in salt water. But this voltaic pile, the first battery, electrified the world of science.
With the battery, you could now perform a variety of experiments that had never been possible before. And these experiments were done immediately.
Just weeks after learning of Volta's discovery, 2 British scientists used a crude battery like this one to split water into its 2 elements, hydrogen and oxygen.
The electric current was somehow breaking up the water into its components.
Even more surprising, the hydrogen collected at the negative electrode over here, and the oxygen collected at the positive electrode over here. Why would these 2 elements show a preference for opposite electrical charges? Intrigued, Davy set aside his research on gases, built a voltaic pile, and began doing his own experiments on electricity.
And it became Davy's big pursuit in life. What could this electric current do?
Volta has given us a key to some of the most mysterious recesses of nature. Till this discovery, our tools were limited. Now, the possibilities for chemistry seem boundless. It's like an undiscovered country. A land of promise.
Davy had just begun to explore that land when opportunity knocked. His book on nitrous oxide had caught the attention of the founders of the new Royal Institution in London, who were looking for a director for their chemistry laboratory.
And that book had such impact that it was read in London, here at the Royal Institution. It's very, very precise. It's measured, it's quantitative science, and they thought, this is the man we must get.
Still only 22, Davy set out on his next great adventure, leaving Bristol in 1801 for the city he called the great hotbed of human power.
When Davy arrived, his patrons seemed to be a bit taken aback to find this still rather raw country youth. But his natural eloquence must have come through and eventually charmed them.
One of the missions of the institution was to offer public lectures meant to stimulate an interest in science among the London elite. For this purpose, a theater had been installed in the institution's building on Albemarle Street. Davy started out as assistant lecturer, seen here helping his boss give a dose of laughing gas to one of the patrons. But with audiences shrinking and the institution's fortunes flagging, Davy was quickly promoted to the top job.
Nothing is so fatal to the progress of the human mind.
Determined to make the most of this opportunity, he set out to make each lecture seem spontaneous.
But to do spontaneous, what he did was prepare.
As to suppose that there are no new mysteries left in nature.
And he would read through, in front of his assistants, drafts of the lecture to see if it would work.
Who would not want to learn the most profound secrets of nature? To ascertain her hidden operations?
The moment Davy began to lecture, the audiences packed in.
Science has done much for man, but it is capable of doing still more.
He had people absolutely lapping up what he was pouring out.
There were other chemists giving public talks elsewhere in London, but none held a candle to Davy.
He must have directed his bright eyes around his audience so that they felt really drawn in and mesmerized. And he would do dazzling experiments that he carefully rehearsed with his assistants the night before, so they always worked.
And people gasp, and they cheer, and they clap at the end of a demonstration. It's so brilliantly done. And these lectures became hugely popular. They were the most terrible traffic jams outside the Royal Institution. Albemarle Street became the first one-way street in London because there were so many carriages bringing people to listen to his lectures.
He was young, he was handsome, he was eloquent, and there were a number of young ladies in the audience.
And they're all in the front rows making notes, but hanging on Davy's every word. Among the lecture notes in the Royal Institution archive are these little billets doux, little love letters, often signed with a pseudonym, and poems to him.
One of his female admirers invited him to dinner, noting, "Those eyes are too fine to be forever gazing over crucibles."
I have audiences of 400 or 500 people, many of high rank, and I suspect that some of them may become permanently interested in chemistry. This science is becoming the fashion of the day.
Davy's success as a lecturer and entertainer brought him wealth, prizes, and acclaim. But he was growing impatient. Giving popular lectures was no way to become the Newton of chemistry.
By 1806, he'd established enough of a reputation, and he knew that his work was supporting the Royal Institution. He could say, right, I've known your work for the last 5 or 6 years, now I'm going to do my own work.
An invitation from an organization once headed by Newton himself gave Davy the perfect chance to show what he could do.
He was asked to lecture not to the Royal Institution, but to the Royal Societies, the top scientific group in the world. He needed to produce some dramatically original science.
With this goal in mind, Davy dived into the subject he'd been itching to return to ever since Bristol: electricity.
Up to now, we have studied electricity only in its most powerful form, lightning. But its slow and silent operations on the Earth's surface may prove more important.
From his early experiments, Davy had learned that an electric current could pry apart the hydrogen and oxygen atoms that made up water.
You can use a battery to unbond things and find out what the different elements are.
That gave Davy an idea. Could he use a bigger battery to tackle substances that were harder to break down?
This is something you can do with this new source of electricity. If a small battery gives you a small effect, build a larger one and you get a larger effect.
As the target for his experiment, Davy chose caustic potash, a substance derived from wood ashes collected in a pot. Chemists had long suspected it contained an undiscovered element, but no one had been able to break it down into simpler stuff.
He believed that if you could apply a charge to it in some way, you would discover something about its inner nature.
So Davy constructed a really big battery because he wanted to see whether potash could be decomposed into its elements.
Davy was thus able to use the resources of the Royal Institution to undertake scientific research, which had never been the intention of the founders of the RI.
But by the time he began the work, his Royal Society lecture was only a month away.
Shall we? He committed himself rather recklessly because he didn't really have much time.
Would this new battery be strong enough to reveal what potash was made of?
Working at top speed, he tries various ways of applying the charge.
Davy first tried putting a current through a mixture of potash and water. All that did was split the water into hydrogen and oxygen.
Do you see anything?
Leaving the potash unaffected.
And then he tried with dried potash. And again, nothing happened.
Finally, he moistened the dry potash just a bit before applying the electricity.
Dry potash won't conduct electricity, but when I added a little water and applied a strong electrical current, I soon observed a vivid action. There was a violent effervescence and small globules.
It sweats forth these glowing, shining globules.
They have a metallic luster, very much like mercury, and some of them exploded and burnt with a bright flame. I realized these globules were the substance I had been searching for.
And this is a new element, in fact. It's potassium, one of the crucial elements for life, and he's discovered it. There's a wonderful description made by his assistant, who was actually Edmund Davy, a young cousin. He said, the professor became a boy again.
When he saw those globules of potassium burst through the crust of potash and catch fire, he couldn't contain his joy. It was some time before he could compose himself and continue with the experiment.
And you get a sense of this huge excitement, doing things under pressure, not quite knowing what will happen, whether the damn thing will explode. And then suddenly the unknown reveals itself.
The atoms of potassium and oxygen, so firmly glued together, could be separated by electric current in the same way as those oxygen hydrogen atoms in water.
The very next day, Davy used the same method to pull apart caustic soda, or lye, to reveal another new element, sodium. These two new metals were so soft they could be cut with a knife, and so eager to recombine with oxygen that they gave Davy the perfect demonstration for his next lecture.
Are you ready for anything? All right.
Davy had turned electricity into a powerful tool in the search for new elements. The year after discovering potassium and sodium, he used his battery to isolate 4 more elements, and chemists all over Europe seized on his technique, sending the number of elements even higher.
Sometimes the progress of science is due less to our intellectual powers than to the tools at our disposal. Nothing promotes the advancement of knowledge so much as a new instrument.
Exciting as these discoveries were, in time it would become clear that Davy's greatest contribution was his insight into one of the biggest questions in chemistry.
Somehow, the particles of matter have to be glued together to form molecules, and it was a complete mystery as to what this glue might be. What Davy has had, in effect, is a big idea.
If electricity could pry apart the atoms in water, potash, and soda, might electricity be the force that stuck those atoms together in the first place?
Is electricity an essential property of matter?
Perhaps electricity, with its plus and minus aspects, could be this kind of glue.
In every case that we know of, substances that combine with each other have opposite electrical states. And perhaps this is the reason they're attracted to each other. Because opposites attract.
It looked as if electricity might play in chemistry the sort of role that gravity played in Newtonian physics.
Remember, he thinks of himself as on a par in some way. He's going to be the Newton among chemists. In a sense, he does eventually achieve that.
In the 18th century, electricity was mostly complex, like making somebody's hair stand on end, attracting bits of paper and so on. Davy showed electricity is a fundamental aspect of matter. Electricity is what holds us together. It is the glue that links the particles of matter. And therefore, instead of being rather aside, electricity is going to be one of the really central features of science.
It would take more than a century for other scientists to figure out electricity's role. But after Davy, there was no doubt it would be one of the keys to solving the mystery of matter. Next time on The Mystery of Matter.
Figures out something rather extraordinary about the elements.
Their eye is immediately struck by a pattern, a regular change in horizontal rows and the vertical columns.
He had discovered an absolutely fundamental principle of nature.
My mother made the measurements over again, 10 times, 20 times, until she was forced to accept the results.
I proposed a new term to define this property of matter, radioactivity.
Major funding for the Mystery of Matter Search for the Elements was provided by the National Science Foundation, where discoveries begin. Additional funding provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education, and by the following.
There.
Can we work on our, like, something?
Yeah? Yep.
Does it matter what table?
Is your class next or not? If it's not, it doesn't matter at lunch. If it's your class, next time you come to class, you have to use your own table, but at lunch, it doesn't matter what you say.
I did, first of all.
You guys are working hard, isn't it? you figure out what to do with it?
I think so.
You can change the shape a little bit more if you want. use it, actually, one of the clues says you can use for, at least two things. You can use for whatever you want.
I know what this was. I know, I saw that. Wait, did I drop the same rock? I don't know. Oh. Oh, shoot, you're right. Measure the mass of that one. It's true. It's wet though. I'm so sorry, it completely slipped my mind.
Damn, what? I put the test back there. It's on that last table. You can bring it up here if you want to.
Okay, I'll put my phone in my bag.
Okay.
And I'll just sit back there.
Okay. Remember I told you it was going to take the whole lunch period?
What'd you say?
Remember I said you need the whole, all right, go ahead and do it though. You have your flash card, your index card with you?
Oh, this is what he threw at me. You and your apples.
There's one on there. Look on the last page. And if you just really like this one a lot, you can come up here and sit up closer if you want.
it like doesn't have the Roman numerals, it's just like naming them. But
Okay. So here, if I give you the formula, you have to give me the name.
Yeah.
Now, type 1, you never use Roman numerals
Yeah.
for type 1. But you would, yeah, you would have now. This asterisk says you have to use ich and us. Those are the only two in the whole test you have to use ich and us.
okay, I was just wondering because this would be like lithium too.
But
that-
remember,
oh, it's a metal.
Only non-metal, non-metals, do you ever even look at those to name them, so. I mean, I shouldn't say looking, but you don't have to figure it out on type 1. The one I wrote in there was the one that I gave everybody for free. That the one I written in black, that's free. We could have a girls' club here or something.
Yeah. We do have this bus break.
I believe. Mr. Feeney, don't we have this class next?
Yeah.
Yeah, yes. But they're working on some other stuff.
Oh, that's the objective.
Yeah.
Oh, it probably is. I'll get it. Okay. I'll be there. I'm sure you will. Hey, it's not even hours. It's bad Fred. E. coli. That was great.
You know.
I know. I know. Not when my brother got it, they didn't.
Do you like to look at it sounds?
No, it's just a picture of what it looks like. Come at me, bro. That's okay. No.
Push past.
I think it's like,
Go all the way around.
not all of this, the whole place. Dang it. This is George, right? Yeah, but that's girl. No. You know how he's girl. You won't be able to. So it doesn't get it, no. This is how it's girl. What the heck?
Nice turtle.
I thought you were gonna go to the window.
Exactly, misdirection.
But you can't do this though.
Probably right. I'll probably drop it. This is our class, right? Yes. That's how much juniors are. We just work on it. Oh, we're gonna, the rest of the defense. Is density detectors still have partners, Mr. Feeney?
Yeah, they always have, I try to have at least 3 in a group. So, cause they, if one person's gone, that's no good.
Yeah. 5-year-old cousin.
No, why?
You answered your own questions very easily by your action. Integration is not on the problem set right now.
Hopefully not.
What
Well,
differentiation is?
If it is on there, it won't be like super hard stuff. It would be like the basics, like what do you do with this basic problem?
Honestly, after the last one, I skipped a lot. Oh, that's Egypt.
You just shared right there.
Because of the free response. I thought we were gonna do free response together.
Okay. You'll be alright.
I just hit her. She was back here. Yeah, but I thought we were gonna do one together.
I don't even know how to respond to that.
I should talk about doing that. The funnel, that was a pretty close question. I never did it together. Yeah, but we did it.
Not maybe right away.
Oh, it's very fine, bro. It's kind of no, the problem's right there. The problem is that we're about to take.
No, maybe not.
Yeah, but there's a free response.
Are you never guess my least favorite kind of people are?
You already told me.
Yeah.
5-year-old cousin.
Exactly. Go out of your way to make your life hard.
That's crazy. Of all the people who have ever been, 7 are alive for every 93 years. That's crazy.
Oh yeah, this book.
That surprises me.
There's the exact number.
People like China, like,
Oh, I guess that just means other places.
well, actually, I think it's increases though. I think we got, they got rid of the
Wait,
rule or
what's
they.
it?
I don't know what to do with this. Yeah. No, we are. We are. Yeah, we are. You tell.
In the back. Not the backpack, but in the back.
Yeah, I was just checking.
Oh, yeah, yeah.
She was 16.
Okay. It's not that long.
You wanna read like 5 years, man, that's crazy. Oh, yeah. 5 years. Age 26, of people 26 are from 14 and 40 years. 66 are 15 and 64 and 8 are 65. 85 people out of 100, 85% of rate. That's crazy. I think the majority of middle-aged people in America were adults. It's empty. It's empty. People from Asia and Middle East, 61% are from Asia and Middle East, 19% are from China, 18 from India, 4 from that's not 61. Total.
Yeah, I think that's
Total,
60.
and then 90% of them 61.
Yeah, yeah.
Oh.
That sounds really stuck in my head for the rest of the
Maybe
day.
one from Europe. People, 9 people from South America, 2 from Brazil. 5 people from North America, 4 from the US. Names are, one person's named Lee or Lee, one person's named John, one person's named Coleman, 2 people have the name Mohammed. Sexuality 90% are hetero, sexual 10% non-hetero. People, the world is 100%.
If you took every person and said, that's only 100, what's the relative, if everybody, no, if 7 billion people or 100, how many people would have a toilet? How many people?
12 people speak Mandarin, 5 people speak Spanish, 5 speak English, 5 speak Hindi, or 5 people speak No, that's just the, that's the people. went to that guy's husband and told him that Gatsby was having an affair with his wife. So he goes and shoots Gatsby.
Yeah.
Thinking that that's what happened, but really it was Tom.
Yeah.
Also,
that happened to
also
himself.
Daisy's the one that hit Wilson's wife.
Yeah.
drown himself in the pool?
No, he got shot.
He got shot and fell into the pool.
Wait, but didn't
Wilson?
guy,
Wilson?
didn't Wilson die too?
Yeah, he shoots himself.
He shoots him, and was he also in the pool, or is he just? No. Oh,
63%. The atheist, there's no candle, that's funny.
Do you guys understand like what Gatsby did that made them all like really, like he ran the food place.
Well, it's
But then he also had like some other business that they didn't mention.
It's the fact, the whole,
I don't think
reason
that's
everyone got
really-
angry is because so Tom was cheating on Daisy.
Yeah.
And then Daisy knew that.
Right.
Tom didn't know that Daisy's, like, so Gatsby started getting into Daisy's life. Tom didn't know that Daisy's having a relationship with Gatsby. Nick knew everything. Tom finds out that Daisy and Gatsby are a thing. And
like,
now
yeah, you can't
in
go
the plaza in the park, which is why he's saying that that was so important. So he gets angry and confronts Gatsby, and then,
But he's like,
kinda
I
saw
know
it on the
you're-
deck.
you're- I
And
know
then-
you're running a business now.
yeah,
so
he was
that-
he was trying to prove to
what's his
Daisy that he
name?
wasn't a good person. But, and then Daisy said that she loved both of them, which made Gatsby really mad.
Because he wanted her
And then
to
she
say that
was-
he didn't love her at all.
Yeah. And then, so then Tom, Nick, and Jordan, left in one car. But apparently Daisy and Gatsby left in another and beat them because they were
Yeah,
speeding.
I know that's.
And ran
I
Brady
just,
over.
there were a few things.
If you ever just want a summary, just watch it out, just like, the great Gatsby movie, it
Oh, yeah.
does everything well.
Makes mistakes a little bit.
Yeah, with DiCaprio?
Yeah.
Yeah.
Like, all the scenes are very
I
accurate.
really never thought, I mean, I think I've seen things in my lifetime, but nothing, usually there's enough people that stand up.
Oh, yeah. I was like, what is he doing? And they're like, oh.
Usually, when I used to grow up.
The way, like, I never got comfortable with DiCaprio saying
Oh,
old sport in the movie, I'm just like,
Question something.
I don't like that for some reason, it sounds weird.
Yeah.
In every single sentence you have to say old sport, I'm just like, that's.
Oh my gosh, you guys think this world of Georgia.
Yeah, they took her sleep though. And you tied to monsters.
I don't think that's true.
Well, as a,
Because if,
it was.
if it was fun,
New York said,
Well, no, it's just thinking, everyone in the entire world.
Point is not the village is real, the point is, out of that
And they made
percentage,
like lists of all.
out of 500 people, only one would have.
That is 20.
Not realistic, feel like everyone is living in the village.
but I just, like, I
You're
get
right.
saying like, I get saying like 1 out of 500 people has a PhD in today's world. But I'm not sure I get making the point of.
I can see some of them, but I just can't.
Well, I was saying that usually it's usually out of 100. This is why they had to say,
I just
please
wonder
that's
if
fine.
they have things.
Because all these things are out of, if there was 100 people that represent the entire world, these are the percentages. Whereas that one was said out of 500.
One, one person owns 48% of the world's wealth and they should number 48% of people live on less than 2 fifty a day. And 60 live on
You know, your index card.
Trust in the government. If you do trust in the government, you do.
Well, it's also, if you think about it, it's not like everyone has the USA government.
That's true.
The whole world. I would think the majority of the other world wouldn't necessarily.
And even like.
freaking, I read that 40% of the world lives in the blue, and the rest does like 40. I think that's pretty small.
I mean, I guess like if you're counting like the amount of space.
This is people.
Yeah, it's just
That would surprise me based on people because China
was like 40%.
I mean, most of Europe's.
Well, India's better.
You're not either.
I know, it's like
Oh, I think you are. I was like, what you are?
Well, what is it down? I guess a lot of you. That's a good question. How many are socialists?
And does Russia really
Alright, welcome everybody. We're gonna actually get into the lab today. Which one?
India's a
Okay. That's a lot of people there.
Yeah, that's a lot.
Alright, so hope you have had a good day so far today. The sun's shining over there. Alright, we have, I don't want to talk too much today, and hopefully, if you had a chance to take notes, and I don't need the notes till next Tuesday or something like that, but watch the videos and make sure you have notes and you turn in. It's a small assignment, but I'll give that first grade of the next quarter. And I did grade the quiz I gave to you, and I didn't want to make a quiz that was any kind of a punishing quiz. I didn't want it to be a punishing quiz or anything like that. So what I did is, when I made it, I actually subtracted from 43. It's a 40-point quiz. I subtracted 43, and that didn't even count the bonus question. So we actually had one person here get a 46 out of 40, something like that. That was pretty high. So I think that's fair. It's also like, because I was looking for a certain word that I think went along with the idea, you might say, well, that word works. Well, it's not a very good, that doesn't work very well for me. And so that's why I subtract from 43 also, because maybe there's one or two you say, well, no, I said pH indicator. Not pH indicator, okay, but anyway. So you might not have liked that I marked that wrong, but by subtracting from 43 and having the bonus quiz, I think it came out to be very fair. I think it did. We had a lot of high grades on it. I knew that. Anyway, that'll be the last grade I have for the second quarter. Should be right there. Okay. Now, today, I'll give those back to you. I'll give those back to you when you're in your groups. I decided to pick your labs for this. There's several things I want to do. Number one, if I can get you to understand what is the idea of spectrophotometry, that's one of my goals. Can I get you to do an experiment with spectrophotometry and make what they call a standard curve? That's another thing. That is a huge idea in science. I find it hard to believe if you went to any big university and you took a chemistry class, I think that would definitely one of the labs I'd want to do if I was a college professor, okay? And you probably will do one like that. So spectrophotometry is used all over the city even. They're all over the place. They used to be, you had a sample and you said, well, let's take it to the lab, and then maybe 2 days later they would tell you how much chloride ion was in there, because they had to do all the chemical tests and get a precipitate and weigh it and dry it. And now they just use light. They just use light and a standard curve. Here in Greensboro, they have the water treatment plant. And what they do is they put a chemical in there that looks for like phosphate, and the chemical will change the phosphate some color. And they take the unknown and say, how much phosphate's in the water today? I don't know. Let's put in the spectrophotometry. They look on the chart and say, hey, it's 5 parts per million. What's the limit? Yeah, if it's over 20 parts per million, we have to do something. But it's less than 20, you don't have to do anything. So I guess that water's okay as far as phosphates. And they can do that like that. They can tell how much phosphate is in that water in seconds, not days. And that's why you're going to see this. That's a really big thing in chemistry. Now, I'd like you also, even though you're going to do the lab that I had given you, the one I printed off for you, you're going to do that one. That's what I want you to do. I also want you to do some research. So you got plenty of time, like 4 or 5 days. Do some research on spectrophotometry. What can you do with spectrophotometry? And then, when you come back and you finish the lab I want you to do, I want you then to take a couple days and say, we're going to do our own lab. We're going to do our own lab with spectrophotometry. Now, if you go online, you'll see some ideas. So what are your ideas that you want to do? Say, oh, I saw one with spinach. I'm going to go buy some spinach, okay? So maybe you want to bring some spinach with your group, okay? So you're going to turn in the lab I want you to do, and then you're going to come up with 1 or 2 labs that you can use a spectrophotometer for, and decide what you want to do with it, okay? I'm going to let you have a little bit of freedom with that. And then after we get done with this lab, I am going to start a completely different thing called organic chemistry, where we build models and things like that, okay? So, but I really enjoy watching you in the lab, and you really do seem like you're applying the stuff that you learned in class. I enjoy that too. All right, you're all the suspense. You think, ooh, group I am, ooh, group I am. It shouldn't really matter what group you're in, because you're in it, right? You're in it. So if you want to make your group really good, you can make your group really good. Well, I randomly picked these, and I tried not to give you the same partners as before, but sometimes that happens. Group number 1, I'd like you to be at table number 1. Did anybody here leave that stuff here? That sweatshirt and cup's been there? Okay, it's not you? Okay, I'll get rid of them. Number 1, Gabby, Alege, and Isabella, and Christina, you're group number 1. At table number 2, that's the one group I had to have more than 3 people, so Sydney's group number 2, and, can't see it, there's, and Kyle, and Carson, and Caleb. That's group number 2, table 2. At table 3, Caroline, and Jonah, and, where's the other 3? Calvin. All right, group number 4 is Jeb, and Gabby, Black, and Alex. And group number 5 should be Tim, and Lolly, and EJ. Anyway, so I think that'll work. Did I leave anybody out? Okay. All right, so you go ahead and, I know. Sorry. I have distilled water stir stations. You'll probably use a stir station. You're going to make a solution, aren't you? Now, we don't need to make 500 milliliters, so I would like you to use the 100 milliliter volumetric flask. Get that? Let's make 100 milliliters. That's all. We don't even need that much, but let's everybody make a 100 milliliter solution. And I have distilled water, and look this stuff here. This is what you're going to make. You're going to make a solution of this right here. And it even tells you the molarity in there, doesn't it? Doesn't it tell you what molarity do? Doesn't it? So if I read it out, so it does. But what's interesting about this, it says cupric sulfate pentahydrate. What the heck is that? What's that? How would you write that formula out? Say it again. Cupric sulfate pentahydrate. Oh, that's a problem. So you're going to have to figure, even though your packet says it's copper sulfate, it's really copper 2 sulfate pentahydrate. I'm going to walk around every table, and you're going to show me some of your calculations on how many grams you think you need to make a 100 milliliter sample, right? To make 1/10 of a liter. And then you show me your work, and I'll say, oh, you forgot something. See? All right. What do you think? I know what to say. So the balance is over here. The 2 electronic balance over here. We can separate those if we want. Now, back here, I think if you could make your solutions in the test tubes, that's what I would do first of all, because you're going to make your main solution, and you're going to have that in a volumetric flask. And then they're going to ask you to make some dilutions. And it'll say, we'll take 2 mils of that and 8 mils of water. How are you going to do that?
Test tubes.
What? Test tubes. Well, I know, but how do you know, where's 2 mils? How do you measure 2 milliliters? First, if you're really good at the teeny tiny base, you could do that. Or, what else could you do? What if you're really good with using the graduated pipettes? What about that? So I have to make 5 different dilutions, and I could use this for water, couldn't I? I could draw some water up here, and I say, you need, what do you need, 2? Okay, what do you need now, 3? You could do that. So But I do want you to give some, I'll give you a little independence on that. Everybody got that? So a little bit independent. But, you wanna mark your tubes. Make sure your tubes, you know which one is tube 1, 2, 3, 4. It's possible you may not get to the spectrophotometers here. If somebody read it and said, I'm gonna get that out now. I wanna find out how to use it now. You can do that. Otherwise, you'll use it the day you get back. But, you'll have to seal these over the weekend, right? So you'll probably use your, parafilm, is that correct? But some of you will say, I'm gonna send one of our people, and they're gonna start using the spectrophotometer. They're gonna see how to use that. All right, does anybody know? Does anybody know what the special name is for the tubes that you put in a spectrophotometer? You know what these are called? It reminds me of a car I wish when I was younger I had enough money to buy. I don't have money to buy now, but anyway. Cuvette. Reminds me of Corvette. But anyway, so these are cuvettes. Cuvettes are always what they call the tubes that they put in. And these cuvettes happen to be exactly 1 centimeter across, and that's standardized, kind of like that. And if you watch the video, you'll know that the spectrophotometer, the light has to go through this part, because this part has all kinds of lines on it, see? So you put your fingers on that if you want, just don't put your fingers on that, or wipe it off. Now, if for some reason, you said, I just didn't have time to watch any of those videos, and I'm going to though. Let's just make the solution today, let's get that done, and then I'll do the spectrophotometer when I get back, how about that? And then over the weekend, you're gonna think, what else could I do? What else could I do with the spectrophotometer? All right, let's go ahead and get groups, and, I don't have a, group 6. I'll put it over here. You have a, graph paper? With a beaker. You can start with a beaker, because a stir bar fits very well in there, and you can get it started, and then you can finish it. Coming behind you, Gabby. The stir station.
Yeah, it's like together. But I assume if you put it in water, like you'll have the H2O.
That stays over here. Let's put that over there. Caroline. How did that even happen? Okay, we're okay. The good news about this is, we actually put this stuff in on to kill owls. Oh, I have no idea. Not kill fish. Now, it's not, I'm still not gonna eat it, but the good news is,
So we need
let's keep the chemicals over here, okay? Let's keep the chemicals over here. Let me get some, cheeses.
So we got
mass of copper 2 sulfate pentahydrate. Let's do that. What's the molar mass of copper 2 sulfate pentahydrate? Are you done?
Are we sure it's 2
sulfate pentahydrate.
I completely forgot, I thought you were. Carson, you say you I thought you weren't in the street, I thought you were.
I just go under.
I said sooner in there.
Alright, you don't have to put your goggles on until you start messing with the chemicals. So if you go over there and do chemical stuff, you can put your goggles on.
So wait, one more solution we have?
So let's see.
What's that? In fact, we haven't got to the procedure, we haven't got to the lab. It says here, oh, you're going to go get a 0.4 molar, no, you're gonna make it. The only thing they didn't know, how many copper 2 sulfate pentahydrate. Okay. Now you gotta figure out how you do it. We got the molar mass. We got the molar mass, okay?
One mole of all of this is 177.6, 1 mole So what do we need to do? What are we looking for?
What's the name of
Budget set.
That's taken from a AP test. That's not, you don't have to read that, I just told you it was done. When it's done, you can say, yeah, I think I understand that AP question from the spectrum of all the volumetric flasks are back here.
Right, so we just need to figure out. I think I know that.
What'd you get? 49.
Everybody figured it out yet?
So in order to need one moles and then that would be in grams. But. The molarity.
Get all the supplies we're gonna need for this.
Have you figured out? Let's see, what's the molar mass?
The whole thing is.
Can you count the 5H2 or not?
Okay, so I think, is that what you got?
When we're figuring out how many
We only had this once in 10th grade, with a hydrated crystal, that is part of the formula. Oh. That is part of the molar mass. You have to add your this up, this, 5H, so that's the molar mass. No, I'm here, to help you, but you're supposed to be doing a lot of this on your own, but I'm just here to help you, so I'm not sure how to do anything. What about the formula? That's copper two sulfate, but what about copper two sulfate? And then the dot, it should be a dot that has zero. Dot in the middle, so it makes 5 from the end of 4. There are 5 water molecules locked up in every H2SO4, so that's part of the more mass, but these are 5 H2. Where did you get that molar area or whatever? That's the molar mass of that. And then you have to make a molar solution, and you're making I'm here to help you. Don't do calculations. Oh. Yeah. That should you cool the water. We got.
Alright, so I just did, I did boil out some cruiser sulfate and water with the
Yeah.
cruiser sulfate makes up 89.86%. So we can multiply this minus 6%.
So plus 10 and then what's?
Yeah, because we only did 18 months and we do 5 months. So then change, figure out for 159, 25, 69.
Now, we're gonna make, I would suggest starting with a deep, because you can put that on a stir station and maybe only put 50 mils of water, because you know you're gonna have more than 50 milliliters, right, of water. And you get it all stirred up, put in your 100 mil volumetric flask, and then rinse your beaker and put that in there, and then fill it up. I don't think we have any. Everybody know where the test tube racks are? Test tube racks. Test tube racks are up here. Test tube racks up here. Alright, two things for sure, have the calculations down. Two things for sure, have the correct calculations. Small one, right?
I got 9.97. That's how much. Ratio, cooper sulfate to total. 63%. So, no, as long as you think there's
Okay, so now, let's see.
Yes. Oh, I'll grab this one again. Yes, yes. Very, very good. I highly recommend starting your solution on a beaker in a stir station and maybe only put like 40 to 50 mils of water. And then, you can always transfer that. Once it dissolves, transfer that to your volumetric flask, rinse out your beaker, and then eventually fill it to the top.
It has to be.
I'll find a rack and see if it says.
Yes.
Pressure or rack below, or actually for work. Somebody can get a test tube rack and get some test tubes and label them. And we don't make the end events yet, we just make them in test tubes and then we'll eventually train them.
That's where the racks are. So like, you like.
Yeah, I'm gonna ask you, you wear goggles as soon as you start testing chemicals, all right?
So we just need the rack.
Yes.
Is this test tube rack?
Find a smaller one. That'd be great.
What would happen if I drank it?
They actually use this in ponds, it kills algae, but it doesn't kill fish. But I don't drink it either. It just saves people. But that's a classic one that they use for, we have corn, and you have algae. Yeah, you probably feel bad. Yeah, use your body. And you're gonna have, I think, about 5 test tubes, so the test tubes are gonna be this small, so try not to get a big route. Yeah, you're gonna have 5 test tubes, and the test tubes are kind of small. Putting two stories.
This is like
Work,
this.
it goes so
Christina, stop drawing my people here right now, right?
This is a long one for some. That's that copper 2 line.
It looks like
Clorox, unless they put a dye in it. Clorox is probably using clear, but they might make it blue, make people feel.
Yeah.
right, I'm gonna put my goggles on because everybody's getting chemicals out now. So if you don't have goggles, go ahead and go get those.
Okay, I'm leaving our test tubes. It says, so right now, I'm right here, with the 5 effects of elements and figuring it out. I was like, that's so big, but okay, now I'm trying to figure out, oh, no, it's gonna be
If you didn't have a chance to read or watch the video, spectrophotometry always includes a blank. So if you're going to make some test tubes, they want you to make 5 test tubes. You might want to make a 6th one for your distilled water blank. Okay, and you can just say B on it for blank or like that. So when you start doing spectrophotometry, you're going to have a blank in all of your samples.
It says, right here, so this is B or distilled water. Okay.
What happened is, that will only hold all of this. You have plenty, then you just give it has to be at least 2/3 full. You don't need to go to the top because we don't need the liquid to get in the machine.
Hey!
I could put at least 50 mil in and get that going. Just a 50 mil. Have you put water with your crystal gel? Just put at least 50 mils in there right now and get it stirring.
So if it's gonna be a higher concentration, it's gonna.
Oh, yes, we don't have to do calculation. There'll be less.
Okay.
From the video yesterday, whatever method you keep on.
Well, we make, it says obtain small volumes of 0.4 solution in distilled water in separate units. Label 5 on the dry test tube, pipettes and compare standards.
What's gonna happen is, I take the screw bar out of here, rinse that off, and then you're gonna transfer that to here. Then, you can rinse the beaker, rinse whatever, you can get everything in here, and your line is right up here, as far as the door. This one does not, produce heat, hardly any heat. That's a great question, so we don't have to worry about the heat of, and that'll be, I bet that'll be completely dissolved in about another 2 minutes or so. So we had you guys tested it, looking real good. You guys are really, really great, you're looking good, I know some of you started out saying, what am I supposed to do? But you figured it out, didn't you? Part of being independent here. Tell me if you need something. Say, I need something. Now, you're getting close there. My own opinion is instead of squeezing the water, do you get really close line? I really use the practice.
Handle cube doesn't
But you
leave
get
like
close.
off edges of the side, dislodge any bubbles, pass that on. Always within the sheet, that light out.
It's a technique.
I don't think we actually because first we have to make all of this. Yes, I guess we will need another rendering. Yes.
Okay, first one is.
Seal them off and then seal that all off.
We'll go, that's two.
Fill this up behind.
What do you think? This looks like pretty dissolved.
So pour this up to the 2 milliliter one and then we'll put it, fill 8 milliliters of water.
You have time? You have plenty of time?
I think it's kind of.
Are you starting to make it? Which method are you gonna use? Graduate cylinder, like that? Now, don't you need one for water? Here's another little technique. If you had a clean beaker, you could actually pour this out into that beaker. It'd be a lot easier to get to it. And you could pour over the beaker. But anyway, and then somebody else could get some water in another beaker.
So that. Pressure water. Water beaker.
Yeah, we'll wash that out. So, we pour that all in.
Now, eventually, you're gonna have to have so many milliliters of water and so many milliliters of that. Probably you use a different graduate cylinder so you have to put a line can. A line can has none of the chemicals, just distilled water. So you try to know, they only tell you to put 5, but they'll eventually tell you to put a blank in the machine. Okay, now, somebody's gonna go, how are you gonna figure out exactly 2 milliliters of this stuff? You're not done yet, you gotta make this first. And then somebody else gotta get 8 mils of water. Somebody could do that right now, 8 mils of water, 6 mils of water.
It's not even.
I can do that right now. Oh, I hate to tell you this, but when you guys do your graph of Beer's law, when you do your graph, it'll actually tell you how good you are in your technique. How good are you at making these solutions? So, tell yourself, we're gonna try to make every one of those dots be on the line. That's your goal.
I'm just going up to this one. Yeah, I like a little lower.
It's not really home.
It's somebody who
That's not all. We cut everything out.
Okay, we're back here. If I ran out, I'll get you some more. Let me know if I run out of anything. Yeah, okay, there you go. Oh, darn. Are these not, are these 10 mil? Hey, wait a minute. Has anybody measured these? Are these little test tubes, too small?
Yeah, I think.
Darn. Okay, wait a minute. All right, let me see what else I have. So those are less than 10 mil? Yeah. Darn. All right.
Is it the minute?
Yeah, little test tubes for certain experiments. All right, my fault. Wait a minute. I made a mistake. The little test tubes are cute, but they're not 10 mil. They're not 10 mil test tubes. So we need something bigger than 10 milliliters. Sorry. I apologize. We'll have to make 5 more test tubes. You can take your blank one if you want. I apologize. I forgot that those were less than 10 mil test tubes. Now, I might add some here. What do you think? What do you think about the idea? We can use big test tubes, or what about the idea of cutting these everything in half and making a total of 5? The cuvettes, let me go measure the cuvette, see what it is. If the cuvette is only a 5 mil cuvette, we can do that. Is this your exact six? We had 8. Okay, the cuvettes only hold 3.5 milliliters. So we could actually just cut these numbers in half, use the still tiny test tube. You get it? One more time. If it tells you to put 1 mil, you put in a half. If it tells you to put in 8 mils, you put in 4. And then your total sample is only 5 because the cuvette's going to hold 3.5 anyway. So you can actually cut these in half, still use the small test tubes.
So we have, y'all have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now, we need to obtain small volumes. Okay. Use pipettes to purify.
Everybody understand what I meant by you can still use the small test tubes, you just cut it in half?
So now we need two different things to measure.
Alright, so everybody understand what I'm saying here?
Yes, okay.
I made a mistake, good enough, but you guys only three and a half, so.
Like the tiny one.
Okay. We need another.
It starts down.
Both of them in half, yes. The ratio stays the same. Alright. No, it doesn't. I put that in.
I think it's just in order to
I put
get
that
so
in.
I'm just gonna give me 1 third.
The other thing about the pipette is, you have to be careful that you don't have air bubbles in it. Like, example, if I had a beaker, I'd probably use a smaller beaker, because see, you know, the bigger beaker, it's only gonna stand up here this way. There's a chance you're gonna get coming out there. So the smaller, oh, that's a good one there, I like that. How do we use it? Okay, so you stick it in there, and you just go like that, and it draws it up. You stop where you want it next, and you let it go, there's 2 ways to let it go, you just push this little trigger just a little bit, it's not a gun. Push it a little bit, and let the air into it.
I just feel like,
They did it in the 10th grade, but they haven't done it for a while.
That's
I understand what I meant by the cut it in half. Yeah. We still use the small test.
so will this, like this column, like on these, be like building the water?
Yes, yes. And that would be a total of 5, it's still the same concentration, because the ratio is pretty Still have about 8 minutes, so tell yourself, we get these dilutions done in 8 minutes. Fill it up. We're gonna be here. Somebody could be doing that. Like I said, one, I'm gonna put in 4 milliliters, and then I'm gonna go get 3, 2, and then 1.
Oh, yeah, I do more water. Oh, here's the.
You gotta know what the big test is. I guess if we wanted to.
And then we can take one out.
But why do you need that and 2 breads? Y'all bunch of equipment hog. What?
Okay, so let's pour.
You're about 1,000% here.
I think we should.
Yeah, because y'all have like 8.
You want to pause the part and then add.
Exactly.
You know why? I know why.
I hope I do. I might have to pump cars that will put
1 milliliter bag and then 4 milliliters.
So like one person ought to be in charge of the water. So I'm started it right now. Another person said, I'm gonna be in charge of the sulfate. And then you'll be able to finish it. But if you sit there and watch her do everything.
This is 6. We can, I mean, we can do.
Yes.
Eventually, she's gonna need, 6 squares of paraffin also.
This is gonna be the water. You do water out of this. Okay, 1 milliliter. For water, sometimes this is test 1. This is just 1, right?
film them like as we get them, so we don't actually.
Yeah, so one person be in charge of water, one person be in charge of, I feel this stuff either. So why do you even get it out?
We've done the
And then the person doing the water, I'm done. One person, okay, I'll catch it. But don't sit there and watch one person do both things. When you get done, make sure your stock solution you made is parafilm with your name on it. And then make sure your test tubes, you can find that rack, keep your rack over the edge, and make sure everything's parafilmed on that.
Caroline, where'd you get the tape from?
Right there.
Somebody took it.
Oh, there's
Somebody
the
took
tape
it.
right one. That it?
There's something on
I don't know what this is, but I'm not there.
This kind of stuff. So when you get back, you have a couple days. One day you use a spectrometer, the other day you kind of do your write-up. And then after that, you're gonna have to do a 2-day lab design. Okay? So you won't have to design your own lab until later. We are down to, unfortunately, time-wise, you're down to about 2 minutes or so. But if you can somehow stay and get this done, that would work. If not, you could parafilm the copper sulfate and you come after school, you come tomorrow. Worst case scenario, parafilm your copper 2 sulfate and say, we're coming back. Or if it's not going to be okay, to get to my opinion, I could just keep parafilming this and then very on the side the side. I can't do my full. And my own opinion is, I wouldn't waste the parafilm on this. I know. And I would just keep this back there. And I put the name on it. Now, because we need to clean up, I need you to go ahead and try to think about wrapping it up. If you have to parafilm your copper 2 sulfate, it's okay. It's gonna be okay. You can make these dilutions on Tuesday. You can make them on Tuesday.
Honestly, I don't know.
Yeah, no problem. No problem with that. Keep that, store that back there if you want. We'll be done. It's okay if you don't have your test tubes made, it's okay. You have plenty of time, alright? We'll give you plenty of time to do this. But you need to start cleaning up, because I have another class coming in here. Okay, I need to start cleaning up now for the other class, so.
I want all 3 minutes lessons. I want all 3 minutes lessons. I've been so honored right now, man. I believe there'll be whiteboards and then 4 would be. It's the heat. No way.
Ian Hornets have Rockets.
Yeah, Rockets, you get 600.
Dude, he are winning.
I got a shot.
Okay, there's a shot. It's a long shot. I hope, hey, Ted, I hope you're playing. I really do.
I love parlays.
Oh!
So it's not if at least one learns to make it.
We just need 4 milliliters after that.
That'd be smart though. You could like make it so 2 or 3. Yeah, at least you get.
Yeah, but that would be so unfair. That would be so easy, yeah. That's like. After the easy. We gotta go over the way, so we're going. 2 days behind.
Y'all are gonna change it. Y'all are gonna have to cut it.
Hi, me too. Yeah, I hope I did. I'm sorry.
I don't even know if we're gonna do check on test. We're doing test. Yeah. She did. What? She did.
I know, but I just.
Good art. I know that this was.
That next cabinet there, see,
Like the nurse missed a few days and didn't know if she had.
That's right there.
Me, Corville, soul.
So Scott, and then we get to go.
So I'm good.
We're gonna go over it and then I don't know if we're gonna sign
That was faulty. Sit here and flash the rain or something. I don't think you can throw. Okay, let me talk to the 11th grade, okay? Let me talk to 11th grade. Okay, don't forget, this project depends a great deal on your integrity, right? And whatever you discover, you discover. You don't tell anybody, you don't help anybody, everybody get that? You don't have to feel sorry for anybody, right? You had to go look for them, didn't you? Anyway, get in your group, try to figure out the clues. The only suggestion I had, the only negative thing I had for you, you're doing a great job finding clues. The negative is, you're not doing enough lab work. So, why are you doing lab work all seriously, right? I'm hurt. No. Yeah, it is. Blue and. And they made a formula solution. No, we're gonna dilute it. They're gonna put in a machine, like you have to figure out if this respect has to do it, it must be this customer, this. Anyway, and they're very independent. I can give them a lab and they have to figure out a lot of things, they make their own solutions.
Did you not see it?
This is ours, right? Yeah.
I don't know. Yeah, it's mine. Sarah, that was, I think you gave us some. No, he gave us such. You wrote the wrong person.
That was very racist, and I ended up getting, mushy. No, mushy.
Yeah, because I was getting it.
Alice, they're gonna break something, and then this one was bad.
Did we find the owner of this sweatshirt and cup? Is that in here?
There's two methods.
Yeah.
I like your enthusiasm. See, look, you are gonna have some times you're gonna get frustrated, but you gotta stay with it. You gotta start looking at clues, thinking about things. Watch your scientific techniques. This one goes before, okay? This is actually very, very mainly coming from, like, this says mass equals, and then I know where you did that, it says volume, but the delta is something to do exactly, it doesn't like this. That's just for you.
So I found. I want to find it. So I have 1, 2, 4, 5, 6,
really hold it down. You can alter it a little bit.
There you go.
Are you looking for, base measurement? Or displacement? But, so what you do is, this Google scale, linear scale, it doesn't say zero, but the left line is zero. So you read straight up one line, and now these others, I would have read something like, 3.7, this, ways of doing that. So two methods of trying that going on.
We tried to transfer California. I literally was like, hey, water, okay, honestly though, I was going to suggest over and I forgot about what. Also, that is. For us to get there. Yeah. Oh, wait, or did I wait? We can put, yeah, we can do the budget, yeah. So we also need over that, yeah. Cause you got the math.
Yeah, yeah.
You're putting in there, this is for that.
Want the card? No.
Yeah, I'm really afraid if you're not doing lab work almost the entire period, there's something wrong, and you're spending way too long writing things down. You gotta get to action, figure out where the criminal is, and then start taking some densities. Okay, this project is not to sit here for day after day and write clues down. Okay, that doesn't take that long, maybe one day, maybe less. You should be doing, I would say if you don't have at least five characters done in a day, you're pretty far behind. You might think about coming in later another time. What's it at? Maybe somebody could say, let's go ahead and do that, let's see what's our next one, let's grab that.
What are you? Oh,
It's a mistake. That missed. Take it out. You pushed it so far that half of it just shot out.